Hello everyone, thank you for coming for my defense. And the title of my dissertation is Learning Hierarchical Representations for Video Analysis Using Deep Learning. So nowadays there are lots of video data in our daily life. What we want our computers to do maybe include we want to find the human face, and we want the computer to tell us how many people and what's action, what's the event appear in these videos. So this is quite challenging task. And the reason is because let's first take the cat and the car classification as one simple example. If we want to classify the cat and cars using a simple learning algorithm, if we directly plot the images on a 2D space just based on the pixel information, we find out the cat and cars images are highly entangled with each other in this two-dimensional space. So it's very hard for us to separate them out. But however, if we think about how humans are doing this kind of task, actually we are first finding some key features from the images, such as the eyes from the cat and the wheels from the cars. So if we base on this kind of key features to plot the images into this 2D space, then we find out it can be very nicely separated out. So the feature is very important in computer vision area. However, nowadays, actually, we don't have a very good eye detector or wheels detectors. What computer vision researchers are doing is trying to hand design the features and capture various statistical properties of the images. For example, if we want to calculate the images of the feature of these images, first we do is we find the edges at 4 orientations, and then sum up the edge strengths in each quadrant, and then we'll just connect these values into a long vector, which will serve as a final feature representation as these input images. There are lots of hand-designed features have been proposed in the literature, such as the C features and the hawk features. So if we think the human adult vision system is actually computing an incredibly complicated functions of the input, and we can try to directly implement most of these functions as we just described, like the manually designed features. However, now the question comes to us is that can we learn these functions instead? Let's reformulate this feature learning problem. Given a 10 by 10 small image patch X, of course, we can simply represent this patch X by flattening this patch and using these 100-dimensional real number vectors. Now the question is, can we find out or learn a better feature vector to represent this small patch X? There are lots of methods have been proposed for the feature learning. Basically, it's originally developed to explain the early visual processing in the human brain. It is like edge detectors. Most of them can be seen as the one-layer neural network. And the input is like the flattened patch X, and the output is like an edge detector. So this vector of this output will serve as a final representation for this input X. So if we plot the weights between which connected from X to A, then we found out actually each set of the weight is trying to capture the edges at different orientation or scale. And several methods such as LISI and sparse coding and RBM. Most of the methods using the feature learning and deep learning are designed for the static images, and not many have done on the video analysis. The reason is because, first, the video is a multi-modalities. It has the audio, scene, and motion in it. And the second is because video has a very high dimensional data compared to single image. The third is because it's very hard or non-trivial to have the constant dimensionality representations for the videos. So in this thesis, we propose to learn the hierarchical feature representations for video analysis. First, we propose to learn these features from 3 modalities and also learn the data-driven concept for the complex event recognition. Second, we propose to learn the hierarchical feature representations for objects, and we serve for the object detection in video task. And third, we propose to learn the feature pairs for measuring the action similarity. In the first piece of the work, we are trying to recognize a complex event. And this work is motivated by the TrackVid MED challenge in 2011. So basically, given the videos above here as training from 15 events, and when we have a test video comes in, we want to find out what is a complex event appeared in this video. For example, now this video belongs to repairing an appliance. This is a quite challenging problem because there is a huge variation within the class. For example, the feeding animal is one complex event, but it can have the feeding a horse or feeding a bird. And there is no user tag data. Also, the similarity there is a similarity across the event. Let's say the parade and flash mob is two complex events, but both have a crowded scene. And also, there are lots of data to train and test. The common approach for this kind of problem will be using the handcrafted features, such as the SIFT, MFCC, and dollars. And also, we can also collect a kind of human defined concept. Let's say this is a 62 action concept we collect directly from the Tracklist 2011. There is some motion about human and some motion about cars and animals. But now the question is, we don't know what kind of feature perform the best within all of these hand design features. And the concept we have right now does not generalize very well to new dataset. For example, we have the action like concept detector for USF11, USF50, but when we try this on the Tracklist 2011 dataset, it doesn't perform very well. And also now we only have 62 action concept. The question is, can we enlarge this? Can we get a larger scale of the concept or transfer it to other modalities? Also, now the question is, can we automatically discover the semantic concepts from the Tracklist dataset? So we propose a bottom-up unsupervised learning method. We use the topographic independent component analysis to learn the low-level features, and we can have a good feature invariance property from this framework. And then we use the deep belief network to discover the data-driven concept. Basically, we use the DBN to denoise the histogram and reduce the dimension of the original histogram. So here's the framework. Given the long videos, we first divide them into short clips. Each clip is 5 seconds. And then we use the TICA to learn the features from 3 modalities automatically. Basically, we learn from the audio, learn from 2D scene, and learn from 3D motions. And then based on the TICA learn features, we can represent each short clip using the histogram, background word histogram representations. Of course, this histogram is in a high-dimensional space, and then it has lots of noise in it. So we further use DBN to denoise the histograms and embed them into a lower dimensional space. In the low dimensional space, then we can use the k-means to do the clustering of the clips, and then each group we call it a data-driven concept. So finally, this long video can be represented as the data-driven concept detection scores. Here is the TICA feature learning. So basically, it's a 2-layer neural network. The input is the flattened image patch or the video patch. We call it X. And then the first layer we call it a simple unit. It is connected by the weight W, and which the weight here is what we want to learn. The second layer we call it a pulling unit because it's pulling from this P is pulling from the simple unit by hard-coded the weight V here. So basically in this neural network, V is already fixed, and we only need to learn this W. By learning the W, we just simply minimizing the activation, the summation of the activation on the pulling unit P here. Here we show the learn filters using the TICA from 1D audio. This is 24 filters learn out of 600 audio filters learned directly from the Tracklist 2011. And we see here different filters is capturing different frequency and magnitude information. And this is 2D image filters. It had, we show 144 out of 600 because it's learning from the RGB color informations, so it can capture the color edges. And this is the 12 3D motion filters out of 600 filters. So the size of it is 20 by 20 by 10, and we can find out the filters is actually capturing the motion information along the time. So basically, each row here is one filter, and each small patches here is one frame during the time. So after we learn the TICA features, we can calculate the features for each clip. And then we will do a k-means quantization to find out the code book. And then each clip can be represented using the bag-of-word histogram representations. Because this representation is in a high-dimensional space and with lots of noise, so we further build 3 stacks of the restricted Boltzmann machine. And this stack we call as deep belief network. And then we'll embed this histogram into a lower dimensional space. Then in that space, we'll do a k-means clustering to cluster the video clips into different groups. And then each group we call it a data-driven concept. Here we show some data-driven concept automatically found out by our algorithm. And this is a 2D scene concept. So basically, each row here is top 8 candidates found from each group. So here, the first row here is showing a kind of like an outdoor grass scene. And then this second row is about the vehicle tire, some about text and the outdoor snow. And like the last row is really hard. It's really hard to tell what the data-driven concept scene it is. And here we show this is the data-driven concept, the 3D motion concept. And like some is capturing the crowded scene, like people are dancing and people are walking. And also like here, it's really hard to tell. To compare the handcrafted features versus the automatically learned features, we first did the experiment on the UCF YouTube dataset, which has 11 actions in it. And we show here, as you see, the right one. This is the handcrafted features, motion boundary histogram, performed the very best. However, if we further did the experiment on the 62 action concept from track V11, this is more complicated dataset than the UCF YouTube. And now we see that the TICA 3D is performed much better than the MBH now. Also, if we did the experiment on the 15 multimedia event dataset, and we use a tenfold cross-validation, and we see that the combination of the learn feature from audio, scene, and motion is much better than the combination of the handcrafted features. So this somehow tells us when the dataset become much more complex, maybe it's better to use the learn features instead of using the handcrafted features. And also we show that the recognition result along the different number of the concept using different kind of features. This is the learn feature from audio, and this is the learn feature from scene, and this is the motion, the learn motion features, and this is a combination of the 3 learn features. And we see that around the number of concept equal to 3,000, we achieve the best performance. And also, this is a comparison with the hand design features. And the interesting here is about if we fix the number of the data-driven concept equal to the 62, so the hand-picked concept detector is performing much better than the data-driven one. However, if we can increase the number of the data-driven concept, our performance is better than the hand-picked one. So this means in this kind of complicated dataset, using the large number of the concept will help the event recognitions. And here, if we treat the RBM as a simple dimension reduction method, manifold learning method, then we compare with RBM with PCA, IRE, and eigenmap. And we show along the different along the dimensionalities. So we find out RBM performed the very best than the other 3 manifold learning methods. Also, we compare if we discover the data-driven concept based on the 3 modalities jointly, as the dark blue bars show here, versus the concept is discovered on the modalities separately. So we find out if we discover the data-driven concept separately, it's better to find them jointly together. And overall, our proposed method is around 10% better than the baseline method, which is using the hand design features from 3 modalities. To summarize, In this work, we propose to automatically discover the low-level features and concepts from 3 modalities. And we do not need the hand design features or the explicit concept detectors. And the take-home message for this work will be, learn feature will be very important for complex data sets, and the large number of the concepts will help the event recognitions. So this work is a purely unsupervised learning method. We don't need the label information to learn the features and the data-driven concept. And it is suited for the big data without labels. However, in some computer vision problems, actually we do have a few label information. So what should we use for the use, and how can we use this label information? So here comes the second piece of the work. In this work, we are trying to impose the label information into the feature learning algorithm. This work is motivated by the object detection in videos. So the problem is, if we directly apply the generic detectors on specific videos, we found out at several frames there is a misdetection. And the challenge here in this problem is, actually we do not have any training example to retrain this generic classifier. So the question is how we can directly adapt these generic detectors to videos. The idea will be, instead of retraining this generic object detector, we want to directly refine the scores from these detectors. And based on the observation that objects in the video share similar features, here is one example. One person from town center dataset in different frames. Although this person have different viewpoint or pose information, but the color information or texture information is consistent along the frames. So in this work, we propose to learn the features using a discriminative plus generative method, and we learn the feature hierarchies. So given a long video, we first apply these object detectors on each frame, and we can get a substantial number of detections together with the confidence scores. Based on the confidence score, we divide these detections into 2 sets. One is a confident example set. So here, basically with a very high score or very low score, basically means that we believe there's a human or non-human, object or non-object in it. And then also, if the hard example is collected of the detections which has a score has an intermediate value. So basically, we don't believe whether there's an object or non-object. And then from the confident examples, we will learn the good features and classifier, and use this learn classifier to rerun it on the hard examples, get a set of new detection scores. Then based on the new detection scores, we will pick up some confident one, and then put them into the confident examples, and then retrain this classifier, this feature and classifier from the new confident examples. Then we'll do this iteratively until there's no hard example can be picked out into the confident example set. Here is a basic building model, which is Auto Encoders. It can be seen as a one-layer neural network. The input is still the flattened image patch, and the output is a feature representation. Also, it's like a simple, we call it a simple unit. And we want to learn this weight W. If we call this hidden unit as H, then we can learn this W by minimizing these objective functions. So basically, we are minimizing the reconstruction error of the input X with the reconstructed X prime. And Z is a regularization term. To model this Z, we further add a second layer. We call it the pooling unit P here, by hard-coded the weight V, which is pulling from the adjacent simple unit, and still the only weight W is what we want to learn. To learn the W here, we're still minimizing the reconstruction error as a basic autoencoders, but we add another term, which is a sparse term. So basically, we want to minimize the summation of the second layer's unit. And on top of this is previously I just described the sparse autoencoders, and this is a purely generative feature learning method. Basically, it means given the input X, we can learn this W based on the reconstruction error, and we do not need any label information. But actually, in this case, in this problem, we have the label information. We know from the confidence set, some is human, some is object, some is non-object. To further impose the label information, we put another layer. We call it C. And then this is connected from P to C is using this classifier weight T. So now in this network, we want to learn the W and the T jointly. By learning, so we will minimizing the this objective function. So basically, it's minimizing the predict label with the ground truth. Sure.
Can you explain the pooling units a little more? What they do exactly?
Okay. So the pooling unit is trying. So you see here, once we have we will initialize this weight W here, and then we'll get a hidden unit response, and then we'll do a square, and then do a summation. So basically, let's say this red pooling unit is pulled from the two adjacent simple unit, like this one and this one. So basically, do a square and summation, and then do a square root. So basically, this pooling unit is trying to, if you see this equation here, this pooling unit is trying to make achieve the feature invariance of the learned features. So if we make this, so basically here the square and square root is making this pooling unit to be sparse. And then if we impose this information, then it will saying that the learned feature in the same subspace will have very similar look. So basically, they detect all the edges at a similar orientation or similar scale. Okay, so we have described the generative feature learning and the hybrid feature learning, and we want to because this framework is learning the features iteratively. And at the early stage, the data does not capture the whole distributions. Also because this is a semi-supervised framework, and to avoid the drifting problem, we further propose to use the generative plus discriminative way to learn the features. So basically, we are minimizing the objective function, which has a generative, also the discriminative term. As described, if we can use a hybrid learning method to learn the first level filters from the input image, and then we'll use these learned filters to do a convolution on the input image, and then get a set of feature maps. Then based on the feature maps, we can do an average pooling to get a first level pool map. And then using the same technique, we can, based on this first level pool map, to learn the second level filters. And then also we'll do a convolution to get the second level feature map, also the second level pool map. So the representation of the input image will be the concatenation of the first level pool map and the second level pool map. And in the real experiment, we did 3 levels, these poolings. And we have done an experiment on the 4 human detection dataset and 3 horse dataset from YouTube. And we use a par-based model as a generic detector, and also we use the detection scores. Here are some other setup for the experiments. And here is this detection result. The green one is the original par-based detection, and the red one is our refined one. And this is on the PNL parking lot videos. And later you'll see, sometimes we can find out the misdetection. As shown here, the red one detects the missed one, and sometimes it can fix the false positive. And this is the Oxford dataset. Still, the green one is the par-based model detection result, and the red one is our detection result. Still, you can fix misdetection, and sometimes can find out the false positive, like here. And this is the horse detection from the YouTube dataset, we collected from the YouTube. And the green one is the original par-based model, and the red one is our detection result. And the horse one is much harder than the human detection, because the appearance of the horse is very different based on different viewpoint. Okay. Here are more detection results. I'll skip this. And to compare our detection result, we show the ROC curve here. So this is a ROC curve on the parking lot, and this is on the caviar. This is on the pads and the town center. So this blue one is our detection result, and the red one is baseline method. So basically, our method can improve the baseline around like 3 to 4%. And also, we show that what will be the learned hybrid features look like. And this is the learned features from town center, as shown here. And then we show how town center looks like. And this is a parking lot learned features, and this is a parking lot data set. This is a paths, and this is a caviar. So from the learned hybrid features, we found out each feature is trying to capture the specific information from the specific videos. And also we compare the hybrid features versus the generative learned features. This is from the town center, the hybrid one, and the generative one. We find out the hybrid one is more colorful than the generative one. However, if we see the learned features of the hybrid learned feature and the generative learned feature on the caviar, this caviar is more, the generative one is more colorful, because on the caviar, the background is colorful, and the human is just wearing like a black and white clothes. To compare the hybrid features versus the generative features, we show here the hybrid one is around 1 to 2% better than the generative one. And if we use the same framework but using the hand design Hawk features, our performance is much better than the hand design features. And also we show that with the average precision along the different number of features of hybrid feature and generative features, the hybrid features can achieve the best performance around the number of features equal to 400. However, the generative feature is keep increasing until the number of features equal to 800. So this means the hybrid features will be more compact than the generative one. And also, we compare the hybrid features versus the discriminative features. So here, the discriminative means that we only use the discriminative term to learn the features without using the generative term. So here we show that at each iteration, the performance of the hybrid features. We see that along this iteration, the hybrid features is improving the baseline of the generic object detectors. And also, if we only use the generative term, it's also increasing. However, if we only use the discriminative term, so it's decreasing, because the discriminative term is overfitting to the confident example set, and it causes a drifting problem over the time. And here we have shown the low-level learned features. Now we show the higher level what the model looks like. And this is the visualization of the top layer. So here is a town center. I hope you can see like a human body shape. And this is a learned from parking lot. And this is the model learned from pets. And this is caviar.
How do you generate this?
Okay, so this is what we have discussed. And this is basically it's not from like purely generative from the top to down. This is I got all of the neurons response. Like given the input, and I got a neuron response. And then if that response is high, I keep this image as input. And then I do an average of all of the input, which can give this neuron as high response. So this is how we visualize the model. And also this is a visualization of the horse model. And hopefully we can see there is a horse here.
Horse or horse?
Huh? Oh, sorry, horse, H-O-R-S. Sorry.
But this doesn't look like a horse. Does it look like a horse?
I think you can see there's a horse head and on the leg. And there's a human somewhere here. And okay, so here is the cognitive result about the human detection. We compare. Remember, we have 3 levels, and here is 3 levels perform independent performance. So we see that the first level performed the very best. So basically, it's capturing the local feature information, the color edges. And then, but if we can combine these 3 levels, we can reach the top performance, which is the red one shown here. And also similarly for the horse detection, we also find the first level is the best. But if we can combine these 3 together, we have the best one here. And to summarize, in this work, we we improve the object detections based on one generic detectors, and we can learn these hybrid features directly from the raw data instead of hand-designed features. And we verify that hierarchical feature improves the performance of the object detection, and this can be a pre-step for detection by tracking method. So in the previous two works, we have trying to learn. We are trying to learning the feature or the hierarchical representations only from one input. However, now the question is, can we learn from two inputs jointly? And what will be the features look like? So here comes the third piece of the thesis, is we are trying to measure the action similarities. So instead of to recognize each action and tell what is the actions in that particular video, now we are focusing on measuring the similarity of the video pairs. So here we want to say, okay, this pair of video, they do not have the same action, and this pair of video have the same action. And these have many, many applications, such as retrieval, K-shot, and large-scale recognitions. And our previous method is trying to either design the features or design the metrics separately. However, we argue that the features and metrics are highly interdependent with each other. Fixing one of them will definitely downgrade the overall performance. And here we propose to learning the features and metrics jointly. So here's a flow chart. Given two input video pairs, we first learn the feature pairs from the video. And then based on the learned feature pairs, we get a representation for each video. Then we will learn the multiple metrics based on these new representations. And this multiple metrics will tell us whether this pair of video is the same action or not. This is built based on the gated auto encoders, which is basically model the relationship of two videos. And we can think one is conditional on the other one. For example, if we have the input video X, and as we described, we use this autoencoder to learn the feature U. But now we have another video, which is video Y, and then we can use the same autoencoder to get the feature G here. But to model the two relationship of the F and G, we further add another layer, and we call it using the matrix Z, which basically this matrix Z is learning the multiple matrix, the similarity matrix. And then the input of this unit E will be the corresponding dot product of F and G. So as shown here, we see that we can calculate this unit H using the response of F and G, and then go through the multiple matrix Z. And to reconstruct the input video X here, we simply use the inner product of E and G, and then go through the feature U here. So if we want to learn this feature U, feature V, and matrix Z jointly, so that we can minimizing the reconstruction error, same with the traditional autoencoder, using the reconstruct S prime and with original input X. Further make this model to be symmetric because we think the video X and video Y are on the same position. So basically we want to minimizing the reconstruction error of X and Y together. And further, as the previous work, we also want to impose the label information into this feature learning model. So we further propose this discriminative learning. Basically, we add this label information C here and use the T as a classifier weight to connect this H to C prime. And then we'll just minimizing the predict label with the ground truth. Also, to learn this whole network, we use a hybrid learning method. Basically, we have the generative term and the discriminative term.
Can you just say, I thought you were measuring the degree of similarity. Is it discrete labels, or is it more like a regression between not similar to similar?
It's kind of like it's not a regression, just a 0 and 1, because here is the softmax.
I see.
Yeah. And we have done experiments on action verification, and we use ASAN dataset. And also we have done the experiment on K-shot. We use HMDB 51 and YouTube actions. Also we have done the experiment on large-scale action recognition. Basically we combine these 4 datasets into one big dataset. Okay, so for the ASAN datasets, we have 3,000 pairs of videos, and as shown here, the red one is the actions not the same, and the blue one is the same actions. And we are using the same evaluation pipeline as proposed in this ASAN paper. here is a experiment result. Remember, we are learning the features and metrics jointly. Now we are only testing using the learned features only. So we see that the hybrid features is performed a little bit worse than the state-of-the-art MIP features. And, but if we further use the learned feature and learned metrics jointly, we find out now the hybrid model is outperform the MIP plus the multiple matrix learning method. As shown here, it's around 1.4% better than the state-of-the-art. Sorry. And why is not showing? Okay, so here we show what will be the features look like. Previously, we are learning the features only from one input, and we learn the features like the edge detectors. But now we are learning the features from two input, and so we can learn the feature pairs as the U and V we show in the neural network in the network. So here we show this is one pair of the learned features, and each row is another pair, and it's trying to capture the correspondence between each other. And also we show the generative feature versus the hybrid learned features. So basically this blue one is a feature map use the generative learned feature pairs. And each row here is one corresponding action, one videos which has the same action in it. And here we show this red one is a hybrid learned features, the feature map of the hybrid one learned features. And we find out is the hybrid one learned feature is more focused on the action itself to find out these two pairs are the same. For example, if you can see this is same video, but the hybrid one is focused on the people are like doing the shooting actions, but the generative one is trying also capture the horizontal edges information. Also, we did the experiment on K-shots, and this is on the UCF YouTube dataset. Basically, we are only learning from like one pair of the example, 5 pairs of the examples, and we found out the hybrid model performed the best than the state-of-the-art like ISA feature plus SVM. And also, this is a result on the HMDB51, and still our model is performed the very best.
So one question. So two videos should only be counted as similar if the action in them is the same or similar, not if the background or anything else.
Right. So here is action verification.
And is it a human judge that decides this, or this is just you have this data set with the ground truth?
This data set is provided by Aslan. So basically they provide. So basically they provide a data set.
But they have done the pairings as the
Yeah, they done them themselves.
Done the pairings.
Yeah.
Okay.
Yeah. Okay, so also we did the experiment on the composite data set. So basically we combine this KTH with HMDB and the YouTube data set into a larger data set. And we show here our hybrid features perform better than the state-of-the-art MBH ISA features. To summarize, in this work, we propose to mirroring the similarity between the action videos, and we are learning the feature and metrics jointly. And also, this kind of features are learned in a discriminative way, and we learn the feature pairs and multiple metrics. Also, I would like to mention about the computational cost during this whole works. So if we think about, so basically we use the code core which has 3 gigahertz CPU, and then we are using the training sample which has 16 gigabytes, like locating 16 gigabytes in the memory. And if we do for each method, we use 1,000 iterations to make it until it stops. And then, so basically here we show based on different methods the training time, the cost of the training time. And we found out this RBM is the most low one. And the auto encoder, ISA and TICA, they are almost similar. But because the auto encoder is faster and it has a better property, we can build this multiple levels. So that's why later we stay with the auto encoders. And of course, this is the training time. In the testing time, because it's just neural network, it's just inner product, so the time is not that slow. So to conclude, in this thesis, we are trying to learn the hierarchical representations from videos. And we propose to discover the data-driven concept for the complex event recognition. And we propose to learn the object representations in a hierarchical way from the local edges to global structures. Also, we can learn the relational feature pairs and multiple metrics for action verifications. And in the last two works, we propose a hybrid learning method to impose the label information into the feature learning model. And that's almost it. Thank you very much.